So what we set out to do is develop a product that could be used to clean up PCBs in the environment. What we're calling it is a bioamended activated carbon. The name trading we're using right now is Cetamite, although that might change. And this is a collaboration between myself and Upal Ghosh, who is with the environmental engineering department. He also has a startup company called Sediment Solutions, and has worked out very well for our collaboration. And the basis of this product is that product is based on the fact that right now there are no other alternatives for cleaning up PCBs in the environment other than dredging and capping. PCBs are out there in many cases. A best example is probably the Hudson River, which is well known. The presence of PCBs essentially shut down entire fishing industries because of the high concentrations that develop in the animals. Most of the PCBs are down in the sediments. They work their way up through the food chain and they end up in fish and other products, seafood that we use. And right now, the only acceptable practices for cleaning up the PCBs is either to cover them up, which means they're still there, and there's always the risk of storms and so forth breaking through the caps and releasing the PCBs. And the other alternative is dredging, which is a major project going right now on the Hudson River. Essentially, they're actually going through entire areas. They've built huge dewatering stations. They built train lines. They're dredging them up. They're drying them out, and they're taking them to Texas. So they're not getting rid of the PCBs. They're just taking them from point A and moving them to point B. And the other issue with that is that when you dredge, you re-release PCBs back into the water column. And there's always a high risk of, again, having an adverse effect on the fishing industry when you do that. So dredging isn't absolute. You're not necessarily going to clean up 100%. So a number of years, we've been working on cleaning up the PCBs using microorganisms naturally found in the environment. And we had a number of grants, mostly from the Department of Defense, interested in cleaning up bases, to try and identify these organisms, learn a little bit about them, learn to grow them, and find out what their capabilities were. And we've done this for a number of years. We've been able to put them in the sediments. We can actually destroy 80 to 90% of the PCBs within a very short period. So it takes literally months instead of decades to actually clean them up, and this is a natural process. No recombinant DNA involved. So as far as the EPA and regulators are concerned, there should be no problem putting them back into the environment since we haven't modified them. Now the problem we had was getting them into the environment. How do you get all these organisms back down into sediments where the PCBs exist? And that's when we hooked up with Sediment Solutions. They had a product called Cetamite, which were actually pellets of activated carbon and other components. These pellets would be put into the water column, they would go down into the sediments, and they would break down. And the idea was that the activated carbon would absorb the PCBs and keep them out of the food chain. Now, that doesn't get rid of the PCBs are still there. They're just less bioavailable. And so what we wanted to do is take that a step further, add the microorganisms to this process so they would not only absorb the PCBs, but they would destroy the PCBs in the process. And we did some preliminary lab tests with the activated carbon and the microorganisms, and it was very successful. And that's when we were approached by David Fink. We talked about this project with them, and we submitted our MII to try and develop a product where we could actually make these pellets with the microorganisms in them. So you could take the pellets to a site, you could shoot them in, they would go down to the sediments, they would break down, and the organisms would be introduced into the sediments. And that was the basis of this project, to actually produce a commercial product that could be taken to a site and used to actually break down the PCBs. And this would be the first of its kind that exists right now. Now currently, the Biomite, as far as cost, it's less expensive than current technologies. It's about 10%, 15% of what dredging costs, because essentially we just go to the site, we put it in, and we go away, and then we go back and monitor it occasionally. Dredging, obviously, it's a very intense process, very expensive, and even capping is quite a bit more expensive than what we're doing. And as I said before, capping doesn't get rid of the PCBs, and there's always a risk involved after that. Very low health risk with dredging, as I mentioned. You disrupt the sediments, and there's a risk of PCBs being reintroduced into the food chain. With our process, we essentially just drop the pellets in, and they work their way down in the sediment. We don't disturb the environment. So there's, as the next line says, less environmental disruption. Essentially, this is particularly important for environmentally sensitive areas like wetlands. You don't want to go in and dredge a wetland because you're going to disrupt the ecology of the area. With what we can do is we can actually blow these pellets into a wetland without disturbing the wetland, and so it's less disruptive to the environment. Very low carbon footprint in terms of energy use. We don't have a lot of machinery. Essentially, we can blow this stuff in with, there are a couple different mechanical means of doing this. Much less expensive than coming in with backhoes and train cars and everything else. They're not required. There's no management involved. Essentially, you put it in and then you go back and monitor it occasionally. And there's no habitat restoration. Unlike dredging, where you have to tear everything up and then restore everything, you know, we don't disturb the environment. And so it's particularly well suited for sensitive environmental areas like wetlands. This is the product itself. As part of the MII, we needed to learn, not only produce the product with the bacteria in it, show that it was viable and that we could scale it up and have a viable product. That's the scaled up product there, and that's just an example of when we add the microorganisms to activated carbon. This is just from Baltimore Harbor, some sediment we took. So the top line shows non-amended sediment, the level of PCBs, and the bottom line shows after we add the product, the drop in PCBs. In terms of, those are just days, so we're talking months. Whereas if you didn't treat it at all, the Baltimore Harbor, essentially the PCBs are going to be there for a few generations yet. You didn't do anything. So the milestones were, in terms of developing this product, for first to, on a small scale, test the effects of embedding the cells in this product. Now, we knew we could spray the organisms on the pellets at the site and put them in, but the problem with that is you always run into problems at a site. And if you have a delay, then the organisms die off in the process. So what we wanted to do is develop these pellets with the organisms in them using a cold press process, and then try and develop a formulation where these organisms would last as long as possible so that you have a window of time between manufacturing and getting them to the site. So we did this with a small press in the lab, and I'm going to be talking about what we did because we're about to submit our final report in the next week or so. We did meet all our milestones. So we tried 18 different formulations using a small hydraulic press with the organisms. We found 2 formulations that we maintained 100% viability that the microorganisms liked. We discovered they didn't like a lot of pressure, so pressure was one of the issues. Too much pressure and the cells just died off. And these pellets actually have to be pressed together. So we found the right formulation of water, components, and pressure that would allow viability. Next was determining conditions for maintaining the maximum shelf life. And then this came to changing the formulations again. And we came up with a formulation that allowed them 100% viability after 42 days after manufacturing. We've been able to extend this to about 60 days now. So we know we have a 2-month window between manufacturing and getting them into the site. Milestone 3, we compared the effectiveness of the pellets. We knew we could spray organisms on the pellets. We have good viability. What we needed to do was actually compare that with actually our new process of pressing the organisms in. And we did this in sediment, what we call mesocosms, where we take sediment in the lab, do nothing else to it, and we actually have water flowing over the top to simulate the natural environment. We added our pellets to determine how effective they were compared to the old way of spraying organisms on the pellets. And we found that they were completely comparable, that we could press these organisms into the pellets with a 60-day shelf life, put them into sediment, and they were just as effective. So we were successful there. And then finally, we wanted to see if we could scale this up from lab scale. And that was the important thing, because for the environment, we're going to have to produce tons of this stuff. So we arranged with a firm up in New Jersey that does this cold press process. We brought our organisms, all the components, and we actually produced 2,000 pounds of this material. And we're testing that now to see how it compares to the lab bench scale. We found that so far we're up to 42 days. Unfortunately, the MII is 9 months. We only have a window of time, but we're still continuing to monitor that. And so far, we're up to 42 days with viability in the commercial process. So we've met all of our milestones, and we've been successful in developing a product that will maintain viability that we can now use in the environment. And just as an add-on to this, we have a site in Virginia where we've actually taken this product, and it's sitting there now. And as an example of the problem with working in the environment, we went there 2 weeks ago to apply it, and because of the cold weather, the pond was iced over, so we couldn't apply it. But because we have this window of time, we're going to go back next week, and we'll be able to apply the product and see how well it performs in the field. So we've developed a stable biomite product. This is part of this phase 1. We've been able to, in the 9 months, actually demonstrate that we could produce commercially viable amounts of this product. And then we're hoping to apply for a phase 2 once we get this report in and take this further. We're not sure how we're going to structure this yet, how we'll work this with Sediment Solutions. We'll have a separate company. Those are the things we need to sort out at this time. But the MII was instrumental in getting us through this first phase, and we feel now, since there's no other product like this right now globally, we figure there's a real market for this. So our next phase is getting into the more of the business aspects and trying to develop a company or license this from this stage on. And we have, as a result of this, we have 1 patent that was just allowed, and it'll be issued in the next month or 2. And we had some other patents that we'd already had been issued in relation to this, using the microorganisms, scaling them up. And that's all I have.